Hi everyone, welcome to Synthesis Workshop. I'm your host Reem, and today I'm introducing our Cheminformatics crash course taught by Professor Kit Sheong. Frederick is a lecturer at the Hong Kong University of Science and Technology with extensive expertise in computational chemistry. He earned both his bachelor's and PhD from the Hong Kong University of Science and Technology and further advanced his research through postdoctoral and research assistant professor appointments. His work encompasses a wide range of areas in computational chemistry, including reaction mechanism elucidation using DFT calculations, structure and bonding analysis, molecular dynamic simulations of macromolecular systems, kinetic network models, and machine learning in chemistry. Today, Frederick will share his valuable insights into cheminformatics to help deepen our understanding of the field. Thank you, Frederick, for joining us.
Thanks for the invitation from the Synthesis Workshop team. I'm very glad to have this opportunity to share with you some of the basic idea of cheminformatics. I'm Frederick from the Hong Kong University of Science and Technology. Cheminformatics is a very new field, and a lot of the ideas are actually quite different from the empirical view of the traditional chemistry. However, I want to start our talk with the Nobel Prize in Chemistry in 2024. Many of you know that the Nobel Prize this year is actually awarded to 3 scientists who actually work on computer algorithms and a lot of related developments. Instead of actually working in wet lab, they actually spend quite a bit of their time in developing computer models that will help the further development of biological and also material science. So you can see that the use of computer has already led to a lot of scientific breakthroughs, that we even have Nobel Prizes dedicated to these kind of fields. As represented by the work from David Baker and also the AlphaFold team, you can see that David Baker, his group actually work with a lot of designed proteins or other materials with novel properties or structures. And the AlphaFold team has successfully made use of a sophisticated neural network-based model to predict the 3D structure of proteins. So all these are actually examples of using computers for helping our manipulation of atoms or molecules. However, you can see that these are very different views from the traditional idea of chemistry. Chemistry originally is an empirical science. Before the development of modern chemistry, we know that chemistry actually originates from alchemy. But no matter we are talking about alchemy or modern chemistry, all these relies on experiments. So a lot of discoveries, no matter in the discovery of phosphorus or like synthesis of modern drug molecules, most of them are based on trial and errors. So you do not actually have a very systematic development and have a way to design beforehand how we can achieve a certain chemical goal. And because of that, you can see synthetic chemistry is often very labor intensive, they have very low success rate, and very often they are very costly. So the general idea is that if we want to have a breakthrough in chemistry, it will be desirable if we can lower the cost or increase the success rate. If you want to present this idea with something like a Pareto front, you will see that, well, the modern development are basically either pushing the cost to a lower end or pushing the success rate to the higher end, basically turning from this curve to that curve in terms of the Pareto front. So we want to achieve that either with a more clever way of doing experiments or using computer algorithms. And of course, we're talking about cheminformatics today, so our idea will be on algorithms or statistical models. If you are coming from the experimental chemistry background, you might not know why the use of computer will be important. So actually, let's look at the what cheminformatics. Cheminformatics, you can see the word comes from 2 different words, basically chem and informatics. Chem, of course, that means chemistry, And informatics, actually the word might sound unfamiliar to you, but informatics means making good use of the information. Our experiments are also some kind of information. Basically, our understanding of the world could be described by this pyramid, often called the DIKW pyramid. And basically, we are aggregating a lot of data into information. We're trying to abstract information into knowledge, and at the end, we get some kind of wisdom. Experimental results, in some sense, are putting a lot of input in the data side. But in order to get a comprehensive view of chemistry, we need to aggregate different data into information and then further abstract them into knowledge and wisdom. So this abstraction requires analysis, organization, and identifying trends. And all these could be done manually or could be done by computers. Of course, our goal is to lower the cost or increase the success rate. And for cheminformatics, of course, computer models are frequently used. But the most important idea is still to make good use of the information. That's the core idea of informatics. Now, when we talk about using computer in the development of chemistry, many of you might think of the word computational chemistry. But the usual description of computational chemistry is actually a bit different from the idea of cheminformatics. But before that, let's first take a look at how the experimental chemists look at the world. Experimental chemists, they basically consider molecules as input and they try to put them into certain experiments. We believe the black box of the reality, basically the underlying law of nature, will lead to some properties or reactions based on these experiments. The idea of traditional computational chemistry is to model this black box of the reality into some physical model. So we get a not so black box. So here is basically some physical theory replacing the role of experiments. These physical theories could be quantum mechanics, statistical mechanics, other simulations, and so on and so forth. However, cheminformatics is slightly different, although we still use computer. But the general idea is not to have a whiter box. Instead, we want to replace a black box with another black box, you might say. But that black box is a statistical model. Because in many cases, we cannot have a good enough physical theory to describe the phenomenon that we want to study. In those cases, if we do not have a proper physical theory, then maybe the traditional way of carrying out computational studies will not work for us, because if for a certain phenomenon, the timescale or the size scale are not appropriate for our physical theory, then using the computational model in terms of either quantum mechanics or statistical mechanics may not be good enough. However, if we are using instead a statistical model, maybe we do not get a very interpretable result. But if we have a good model of the reality, then we can still make use of this statistical model to predict our properties or whatever reaction result. So this is the idea of cheminformatics. We are basically using a statistical model to approximate the reality instead of using a physical theory to approximate the reality. Now, to facilitate our discussion, let's consider a certain scenario. So imagine you want to design a new catalyst for a particular reaction. So let's see how a cheminformatics view will help us to streamline this whole process. So similar rationale could also be applied to the design of drugs, not just about designing catalysts. The first thing you need to imagine is that, well, if you are an experimental chemist, then when you are trying to design a catalyst, of course, you want to know whether the same reaction has been achieved before. If yes, then of course, you don't even need to design a new catalyst. You can just copy the procedure from the literature, and then you can carry out the reaction that you want. Of course, most of the case that is not the situation that you encounter. Instead, you need to do some experiments. For example, you want to repurpose an existing catalyst, because if you cannot see an exact same procedure, then of course you need to repurpose an existing catalyst before you actually redesign a catalyst. Now, if you actually tried out all the existing catalysts in the lab and it does not work, then you need to resort to actually designing a catalyst. But still, you will start by making slight modifications only on an existing catalyst before you actually design from scratch. So this is the general idea. And even if you are designing some other like molecules like a drug or achieving some other chemical goals, similar idea applies. And imagine if you want to know whether a certain reaction has been carried out before, then you need to read a lot of journal articles, of course. And if you want to repurpose an existing catalyst, then of course you need to enumerate a lot of possibilities. Basically, you need to try all those catalysts that are lying around in the lab. And of course, if you are leader of the group, then you can hire a lot of students to enumerate the possibilities. If you are a student yourself, then unfortunately, you need to carry out a lot of experiments. And if you want to start to make modifications, then that will actually be based on years of experience or intuition. So very likely, you need to know something about the framework or the backbone before you can try to guess what kind of modification will be useful. And if you want to really design from scratch, of course, then you need some sort of luck, because actually it is not easy to design a new catalyst from scratch. Now, these are the view of an experimental chemist. But all these steps will actually apply and correspond to different stages in cheminformatics also. So in the beginning, when you try to imagine how I can find whether a certain reaction or similar result has been reported, based on the consideration of cheminformatics, you need to know where we can find the data, and if we want to document new data, then we also need to have a way to represent our experimental result that is easy to retrieve in the future. And for the next step, if you try to talk about how can we repurpose an existing catalyst, that requires, from the viewpoint of cheminformatics, that requires a way to define similarity between reactions or similarity between catalysts. And in the meanwhile, it will be desirable for you to visualize the chemical space, because you want to find some similar structures or structures that will lead to likely success. When you are trying to make modifications of existing catalysts, you should be able to make predictions, you should be able to validate your models and propose trends. And at the end, if you are so unlucky and you need to redesign a catalyst, then even the design of experiments will be part of the cheminformatics framework. How do you actually make good use of your information and make valid trials is also an important part of cheminformatics. So you can see all these steps, all these rationales of an experimental chemist will also translate to different steps in the cheminformatics workflow. So this is a workflow. You can see we'll start with asking yourself, what do I actually want? Because knowing the goal is important. And then you need to prepare your data. You need to model your data, model the reaction or model the properties, and then make predictions and then guide your future experiment designs. And in all these steps, we're basically considering different parts or different concepts of cheminformatics, like data acquisition, data representations, defining similarities, visualizing our chemical space, making predictions, including regressions, and how do we validate our model, and at the end, guiding our experiment design. In this talk, we'll actually go through the rationale behind all these steps. And at the end, we'll also show you a step-by-step example that you can also try to work on yourself. So let's begin by the first step, data acquisition. But no, not yet. Actually, you should hold your horse, and before you start, you should really ask yourself, what do I want? You need to define your goal very clearly. You might say, okay, if I'm designing a catalyst, then how do I need to define my goal? I will just want a good catalyst. Well, what is a good catalyst? A good catalyst could be good in different aspects, like a high yield, or a high selectivity, or if you are designing a catalyst for an industrial process, then you need to also consider the, say, turnover frequency, turnover number, and some other aspects. Similarly, if you want to design a catalyst for a more general situation, you also need to consider the generalizability. I want my catalyst to not just work for this particular reaction, I also want my catalyst to work on a wide range of reactions. That will be also a very desirable properties for industrial applications. Now, on the other hand, if you want to design a drug, then apart from all these, some of them are useful, some of them are not, we actually have other considerations, like what kind of proteins should we target when we are designing a particular drug to treat a particular symptom? And what will be the mechanism? Should that be competitive, allosteric, or some other mechanism that it interacts with a binding site? Whether the drug is specific, we often want our drug to be specific for a very particular purpose, but at the same time, sometimes uh, a drug that works for several diseases is also good, but that will depend on your goal. And at the same time, of course, you do not want a drug to have other hazardous effects, so we want the drug to be non-toxic. And all these will actually lead to our data acquisition steps. When we're actually finding our data, we need to be able to figure out which kind of data source will actually give us all this information. Of course, if you are doing the experiments yourself, then you can see all those information in your logbook, hopefully. But if you are trying to get the data from a certain database, then you need to figure out database that actually document all those properties that you need. So knowing different database and finding the suitable database will be the first step in a cheminformatics workflow. Then for different goals, there are different curated databases. Like for catalyst design, then there are certain database that is specific for ligand design. Like this Kraken, they're basically a database for organophosphorus, all sorts of phosphine ligands. So there are also some other database for drug design, like Zinc. The Zinc is a database for drug screening. And if you want a larger database, then you can go for PubChem. PubChem are basically collection of chemical data that has been published. Or if you are going for synthesis of like total synthesis or some other organic synthesis, then you might want to refer to some natural product database like this Coconut, that is a collection of open natural products. So you can see there are different databases for many different purposes. And if you are aiming for a certain chemical goal, then you need to find the corresponding database that works for you. Next step is making good use of information. You will say, okay, I'm having a database that's good enough, but the database actually should organize the information in a way that is faithfully representing the necessary information. That is not too difficult. Even your logbook will do that. For your logbook, supposedly you can note down all the necessary information. Now, that is just one part of data representation. The data should also be represented in a way that is easy to search. If you imagine your experimental logbook, that might not be very easy to search because all the information are organized in chronological order. So basically, you need to look through all the logbook to figure out whether you have carried out a certain experiment before, because the information is not organized by chemical groups or the type of reactions. Instead, it's organized by time. So in terms of your logbook, that might not be very easy to search. So that is also the reason why we often want to put everything into a computer database, because then we'll have algorithms that will assist our searching process. Now, that is not the whole part of the story. That is actually another point that is often missed, which is all the results should be organized in a way that is good for retrieving similar results. That is actually quite important, and we'll see why in the coming slides. All these representation will actually also affect the future choice of statistical models. If you're only keeping certain kind of information, then you'll actually affect the choice of your model, like this one. You can see the information, the representation, and the future prediction techniques are all interrelated. So there are certain structure that will only work for a certain kind of representations, and some representations are good for certain regression methods. So you can see they are all related. And if you are making good use of your information, you need to consider basically the whole workflow before you actually choose what kind of information you want to keep or how do you represent them. And you can see that keeping the necessary information is important, but even that step will depend on your purpose. You can see we can represent a drug like aspirin by the formulation. You can see this is a particular formulation of aspirin. And you can also represent aspirin as a 3D structure of an aspirin molecule. You can represent that as a Lewis structure. You can see this is a Lewis structure. Or you can also represent that as an empirical formula. Now, all these are possible ways to represent the drug aspirin. However, you can see that all these representations are carrying different kind of information. So if we are talking about a particular formulation, then we are actually carrying a lot of information, because that is not just about the aspirin molecule itself, that is also about excipients or even the phase of the active molecules or the active ingredients. But if I only represent aspirin as the 3D structure, we are basically discarding the information about excipients, about the phase that actually the molecules are assembling to, and some other informations. And between 3D structures, like the 3D molecular structure to a Lewis structure, then we are also discarding the bond lengths, specific bond lengths, bond angle, or other 3D information about the molecules. We are only keeping the information about whether there is a bond between two atoms, and if yes, what is the bond order. And from the Lewis structure to empirical formula, we'll actually further discard information about structural isomers. So you can see we can represent a particular chemical substance by many different ways, and that actually depends on our purpose. We will choose one kind of representation over the other. You might say, okay, then we will just use Lewis structure. We always use Lewis structure. Yes, in most cases, we do use Lewis structure to represent a chemical information, but there are also cases that you cannot do that. A very interesting example is this one. This is actually Paxlovid, a drug for treating COVID-19, but we are not talking about the whole drug. We are only talking about this white pill here. This white pill contains something called a ritonavir. Ritonavir, as a Lewis structure, is something like this. This is actually an antiviral drug that has been formulated in other purposes, even before this Paxlovid formulation. The interesting part of ritonavir is that in the beginning, when it was first sold in public, it was successful. But very soon, people discovered that the ritonavir formulation is losing their bioactivity. The reason behind is not because of the molecule itself. Instead, it is because ritonavir will assemble in two different phases. Basically, there's something called form 1 and form 2. They differ by their hydrogen bond network and also how they actually assemble in space. If you think that, okay, this Lewis structure is too complicated, you can imagine, okay, there are two different ways to tile this like L-shaped tile. Then these two formations, these two phases will be clearly different. Of course, this is not an L-shaped molecule, but you can imagine, okay, if I have an L-shaped tile, they could be tiled in different ways. And it turns out that originally when ritonavir was sold and was synthesized, it was in Form 1. So originally, like the antiviral property was discovered for the Form 1 ritonavir. But if the drug was stored on the shelf for a long time, then actually it will slowly turn into another form, the more stable Form 2 with a cis-amide bond. Now the problem with this Form 2 is that it is less soluble, which makes it less bioavailable. So people actually see this ritonavir are losing their biological activities, and suddenly it does not work at all. Now, that will be an issue if you are actually making a design of drug compound. And if you only represent ritonavir based on the Lewis structure, then there will be no way for you to distinguish between Form 1 and Form 2. And clearly, they have very different physical and biological properties. So that will be an issue. So you can see it's not that we can always represent a chemical substance by their Lewis structure. There are certain purposes that we need to represent with more information. Now, still, if we are talking about Lewis structure, if we are only talking about Lewis structure, then it's also a good idea to reconsider why Lewis structure is good. Well, Lewis structure at least represents the topology of a molecule. So for all those essential information and functional group that we care, then Lewis structure is often a very good way to capture that. So instead of actually representing a molecule like this vitamin B12 as a 3D structure, if we use a Lewis structure instead, we can even show the similarity between different related molecules that only differ by certain functional groups. So you can see this one, the R here could be several different functional groups. Using a Lewis structure, we can clearly show their similarity. However, using a Lewis structure alone is not good enough. Because if you imagine, if I try to search a Lewis structure, remember that the one bad thing about logbooks, like physical logbooks, is that they're very difficult to search. And when we're talking about Lewis structure, if we are searching a Lewis structure as a picture, that is also very difficult to search. If you don't believe that, you can try to capture a Lewis structure of any molecule and then throw that into Google picture search. You'll notice that actually either you will get the exact same picture or you'll get some random Lewis structure that is not exactly related to the molecule that you want to study. So that will be an issue. So people actually developed a way to represent Lewis structure as a string of characters, which is if you basically have an actual search in some online database or offline database, like this one is the Open crystallography database, then you can also draw a Lewis structure and then make a search. When you make that search, behind the under the hood, actually, it is using a string like this. This is called a smile string. Instead of actually doing a picture matching under the hood, they are actually using a so-called smile string to represent the Lewis structure that you draw. This smile string will actually lead to molecules that are exactly the same as well as very similar molecules. You can see I can actually turn that into a bromide salt. You can see this one comes with a bromine, which you can see from the Lewis structure that I draw. It does not have any bromine atom, but using a smile string, you can even search similar molecules, and that will be important. Now, smile strings is the full name of SMILES is basically the simplified molecular input line entry system. So it is basically converting a Lewis structure into a string of characters by breaking all those rings into a tree form, and then you can linearize it into a string. So the procedure is a bit complicated, but the general idea is that we can actually map all these Lewis structures into a string. And after we can have a lot of strings, then we can easily search them by lexicographical order. Just like when we are trying to look up a word in a dictionary, we basically go for the first letter, the second letter, the third letter, and so on and so forth. We can also do that for Lewis structures if we actually turn them into smile strings. Now, smile strings is a good way to represent Lewis structures, but they are not the only molecular property descriptors. there are a lot of properties that we often want to describe for molecules. We want to describe the number of heavy atoms because, well, that will relate to the molecular mass and might relate to some other properties. We want to know the number of rings that will be related to some steric properties or some other solubility and so on, and number of hydrogen bond donors or acceptors. All these could be easily inferred from small strings. But there are some other properties like solubility or the steric hindrance of a certain ligand, say. Those could not be easily inferred from small strings. In fact, this information will require experiments or some other extra computation. So solubility, maybe you can carry it out in experiments, or there are some other models that you can predict them. Cone angles, maybe you need some like computations in order to determine the cone angle of a molecule. So you cannot determine the cone angle directly from the Lewis structure or from the small string. Now, you can see actually some of these properties are quite important. For example, in the field of drug design, there's something called the Lipinski rule of 5. So they're basically describing some properties that are unlikely to appear in a good drug. So for example, for a good drug-like molecule, there should not be more than 5 hydrogen bond donors. There should not be too heavy in terms of like molecular weight. It should not be over 500. And for the lipophilicity, it should not be too high. Say the octanol water partition coefficient should not be greater than 5. Or there should not be more than 10 hydrogen bond acceptors. So you can see some of these properties could be directly inferred from small strings, like the hydrogen bond donor acceptors or the molecular weight. But say if you want to talk about the lipophilicity or the partition coefficient, then that is not easily inferred from the small string alone, and you might need some experiments or computation in order to determine that. And sometimes you need to represent that as a number, as a separate number, instead of just using a small string. So all these are related to our consideration in choosing a proper representation for our chemical substance. Now, that's actually an interesting thing about representing chemical substance. In practice, if you are an experimental chemist, then you will recognize something called Cass registry number. So Cass registry number is basically a number that will be printed on all these chemical compounds, all these commercially available chemical compounds or formulations. That if you really search this number, like this 1493 136, then you will actually see, okay, this compound is trifluoromethane sulfonic acid. So this molecule is represented instead by this number. So with a number, then that would be very easy to search, and that actually carries all the necessary information because you can search the database and retrieve all those properties related to this chemical compounds or formulations. And so, of course, that is faithfully representing the necessary information. It is also very easy to search because, they are just numbers. And, however, that is not good for retrieving similar results. You might say, okay, that's not important. I can anyway use this Cass registry number to retrieve information about this particular compound. But why do we want to have a representation that is good for retrieving similar results? That actually leads to the second step of our cheminformatics workflow about preparing data to modeling. And that actually relates to the chemical meaning of a representation. And the chemical meaning is actually presented as the similarity between chemical representations. And with similarity, we can then visualize the chemical space. Let's see a concrete example. Well, intuitively, we will think that Cass registry number does not carry the chemical meaning. But why? What exactly does that mean? Well, that actually means the ability for us to determine neighbors or determine similar molecules. If I give you all these 3 Lewis structures, you will immediately recognize the relationship between them. You will see, okay, this one is like, these two are basically enantiomers of each other. This one is a racemic mixture. However, if I show you the Cass registry number of all these 3 compounds, then you will see that, well, while they are related, they are closely related, they do not have any relationship in terms of their Cas registry number. So although all these three substances, they are chemically highly related, but they are not reflected in our Cas registry number. And that will be important for us to find similar molecules, because when we want to make predictions, we often want similar molecules to give similar predictions. Cas registry number would not be a good representation for further predictions. However, when we're talking about chemical similarity, it is not a very trivial concept. Measuring similarity between molecules is not an easy task. For example, if I want to show the similarity, then there are different ways I can show the similarity between molecules. They can share similar chemical properties, or they can share similar structural similarities. And they could mean different things. Like, for example, if we start with this molecule, methanol, we know that if we replace, like from our chemical intuition, we know that replacing one hydrogen with a methyl group will lead to something very similar. So if we replace the proton into a methyl group, we are basically changing from methanol to ethanol. We will expect, okay, they are similar. And indeed, methanol and ethanol, from our chemical intuition, they're quite similar. And we can use this kind of logic to determine, okay, we can actually change from water to methanol by a similar procedure. We can replace one of the proton with a methyl group, then we can change from water to methanol. And they also share some sort of similarity. But we can also replace this proton with a methyl group. Then the methanol will be turned into dimethyl ether. In this case, we will not think they are very similar. Okay, in terms of similarity, we will think that methanol and ethanol are very similar. Water and methanol are a bit similar, but methanol and dimethyl ether, they are not so similar. So you can see that even though structurally we are always replacing one proton with a methyl group, in terms of their chemical properties, they could be quite different. We need a way actually to somehow represent both the structural similarity and also chemical similarities. And in practice, that is also not so easy, but we often use a way to get a balance between them. But from this example, you will see that similarity between molecules is not a very trivial concept. So in practice, many of the structural similarity are represented by something called a fingerprint. And this kind of fingerprint, to a certain extent, will also represent some sort of chemical property similarities. And how do we define the similarity between structures? The idea is that if we have two molecules, like this one and that one, we can actually have share the similarity by looking at the overlapping substructure. So this one is one molecule. This one is another molecule. Basically, we have the aspirin and methyl salicylate. Now, we have these two molecules. We look at their overlap. This overlap will be this red part. Okay, we can see that these two molecules do share the same structure here, with a phenyl ring, with an oxygen here, with a carboxylic group here. So this is the overlapping part. Of course, matching them by Lewis structure is not always easy. So we want to use a representation that can easily carry out this calculation. So to do that, actually, in practice, we use something called a molecular fingerprint. Basically, we are representing the presence or absence of different functional groups of local chemical environments by a bit string. So basically, we can represent the presence of this like pyridine ring and then this carboxylic group and so on by some bit strings, like 0 means absence, 1 means presence. So each bit will represent the presence or absence of a kind of chemical fragment. Then all these will be representing different molecules. And if we want to calculate the overlap between these two molecules, then we can just compare their bit strings. Then we can easily calculate their similarities. So in practice, this is quite effective in terms of comparing similar molecules. And that is actually very important for us to predict and make predictions because we want to see the similar molecules to give similar predictions. Now, then if we have a similarity measure, then we can visualize a chemical space. And like the example here, this is actually an online platform that you can actually input your data set and then visualize the corresponding chemical space. So say the data set you input will carry out will carry a lot of smart strings, like you have a lot of smart strings, and also some properties like soluble, not soluble, toxic, not toxic, or some other like solubility as a value, or some lipophilicity. So you can do all these kind of things. So as long as you input some smart strings and if necessary some other properties, then you can define a distance metric. And then you can use different distance metric to visualize them. And you also need a dimensionality reduction algorithm. And after you get the algorithm, then you can actually project all these molecules into a 2D or 3D space. And in this 2D space, you will see, okay, if I pick a molecule, then I can visualize the molecule. And if I pick two molecules that are very close to each other, you will also see these two molecules share some structural similarities. You can also see nitrogen here with a ring and then with some other fused rings. So you can also see some shared similarities. So that is the whole idea of visualizing a chemical space. And you can see we want a representation that if we have two similar structures, we should have a distance metric that make them close to each other. And then when we try to visualize them, they are still staying close to each other. Now, this also actually has another step, which is called dimensionality reduction. So this dimensionality reduction basically carried out because chemical structure and properties, if you imagine a lot of molecules have more than 20 atoms or even 100 atoms if you have a super big molecule, then their three-dimensional structure actually lies on a very high dimension because we have 3 degrees of freedom per atom, and we have actually 3n or 3n minus 6 degrees of freedom, and that is actually on a very high dimension. And we may also want to tag it with some other properties, like solubility or partition function. Then there are some other properties. So you can see all these, they actually lie on high dimension. However, most of them are actually related. So we can actually map high dimensional data into 2 or 3 dimension, basically a lower dimension, because as human, we can only visualize effectively 2 or 3 dimensions. And then many different ways. For example, you can imagine the dimensionality reduction processes, like if you have something with a higher dimension, here for easy understanding, we are going from 3 dimension to 2 dimension, but in practice, it could be 30 dimension to 2 dimension, but the idea is still similar. So here we have a 3-dimensional data set. You can see this is data set actually lying on a surface that is put in 3D. However, we can actually put our camera on top and we're trying to look downwards. And if we try to look downwards, we will see a picture like this. We will see that all the reds are on right-hand side, all the yellows are on the left-hand side. And effectively, that is a dimensionality reduction process. And this is the idea of the principal component analysis. We are basically viewing our data set from the direction that we can see all the data points are well separated. Okay, they're well separated. Now, this principal component analysis is like taking a picture from a certain direction. So we can see because we are taking a picture, so we are still preserving the distance in some way, preserving the long distance between the data points. But there are some other dimensionality reduction methods that focus on the local similarity, but then ignore the relationship at a longer distance. Those are like t-SNE and UMAP. They are examples of these kind of methods. They focus more on the local similarity in terms of instead of the global distance relationship. So you can see if we are doing principal component analysis, you might still see some global structure. But if you are doing t-SNE or UMAP, you will see some local clusters. This local cluster basically represents some regions with local similarity. But the distance between clusters do not mean anything because, well, they are basically separated into different groups, but between the different groups, the distance do not actually mean so much. But for principal component analysis, if we see 2 points are very far away from each other, then the 2 points are really far away from each other. But for t-SNE, if we see 2 points that are far away from each other, it does not necessarily mean that the 2 points are far away from each other. We can only guarantee that, okay, the points that are close to each other are close to each other in this dimensionality reduction. So there are actually different approaches specific for targeted for specific purpose. So if you want to represent your data set for the larger distance, then you might want to consider methods like PCA. If you only want to focus on local relationship, then you can use some other nonlinear methods like t-SNE or UMAP. Now, some people might ask, okay, why do we need to visualize our data set? Well, we have so many statistical measures, so then we can, well, we can try to deduce, okay, the underlying relationship by these statistical measures. Why do we actually need to visualize our data set? Well, the reason is our eyes are actually very good at picking out patterns, but those statistical measures are not. We can show you with an example. So this is called the Anscombe's quartet. This is a very interesting data set that, well, if you look at these data sets, basically we have 4 data sets here, 1, 2, 3, and 4. Each data set you can see there are several, there are something like 11 data points, and these data points, each data point with an X and a Y. Now, these data points, if you only consider the usual statistical measures, like the mean of X, the mean of Y, the variance of X, the variance of Y, they're all the same. Even the correlation between X and Y are all the same. Okay, so the X, they have the same mean, they have the same variance. The Y, they have the same mean, they have the same variance. For the 4 data sets, all of them have the same correlation. Now, however, from this measure, if you are only focusing on these statistical measures, you might say, okay, then these 4 data sets are similar because based on these descriptive statistics, they do look very similar. But if you are actually visualizing them using your eyes, then you will see something very interesting. So let's look at the first data set. Like the first data set is this one. You will see, okay, we do have a linear relationship, but some noise with some noise. So you can see it's a noisy but still linear relationship. That is our first data set. Nothing very interesting. The interesting part comes when we look at the other 3 data sets. Like the second one, well, your eyes can pick a quadratic-like relationship. So clearly you will see a nonlinear relationship here. But if you are using the descriptive statistics shown in the previous slide, you will say that, okay, these 2 data sets are the same because they have the same mean of X, same variance of X, same mean of Y, same variance of Y, and same correlation. But from your eyes, you will definitely recognize that, okay, this is actually a nonlinear relationship. I should try to fit it with a quadratic relationship instead of a linear one. Now, the same thing happens for the third and the fourth data set. Like the third data set actually looks like this. Like from the statistical measures, you can see that they're still similar. But if I visualize it, you will recognize that, okay, there is an outlier here. So I should probably check this data point, whether there's something wrong with the entry. Should I discard it? And because all the other points, they are basically lying on the same line, except for this one. And the fourth data set, you can see, basically they have the same X except for 1 point. And then they have a relationship like this. And clearly, if you visualize them, then they will actually affect your decision on how do you handle this data set. So this one, you know that, okay, it is inevitable because it is noisy. So I should try to fit it with a linear model, but I should bear in mind that, okay, this is a noisy data set. I'm not going to improve that. So it will be noisy. It will not be very predictive. The second one, I should actually replace the model or replace the linear model with a quadratic model or some other nonlinear model. The third one, I should probably check this point. The fourth one, I should see whether there's something wrong with my entry so that all my X are the same. So you can see that will actually lead to different decisions. So that is the importance of visualization. We should not just stick with the statistical measures. Now, putting that into chemistry, of course, so we are just talking about the information, making good use of information, but we also want to put that into the context of chemistry. So in chemistry, if you are trying to really visualize a chemical space by principal component analysis, then you will actually pick up some of your patterns with your eyes. So the general idea is still visualizing all the molecules in a 2D space. Now, if you actually check the principal component analysis, projecting things into a two-dimensional plane, you will see a picture like this. So this comes from a quite large data set, and you will see the data points are distributed in this way. And what is a color? What the color is that if I color all these data points according to the number of rings, then you will see that, well, actually different ring counts will actually lie on different regions on this projected space. So that also means that this principal component analysis is actually capturing some important information that is also highly relevant to us. So you can see actually how all these dimensionality reduction methods will preserve a certain kind of chemical similarity at the same time presenting your result in a low dimensional space. And if I look at this point here and then try to visualize all the molecules in the region, you will see, okay, they do share some sort of chemical similarities. At least they all have two rings, and some rings you can see some similarities between them. So these molecules that are close together in the reduced space, in this two-dimensional space, indeed share similar structures. So you can see this power of like dimensionality reduction and how we can visualize a chemical space. Now, after you visualize the chemical space, you will get a general idea on what is your data set and how does your data point distribute. So when you are distributing all these data sets and when you are trying to visualize them, then the next step you should do is to make predictions, of course. And when you are trying to make predictions, then you should look at models, statistical models. The simplest one is a linear regression for making predictions. Basically, it is a black box that was a formula inside like this. So everything is basically weighted sum of all these input variables. Now, this idea is linear regression, and it will, as the name says, that give you a linear model. So this is the simplest one. So from one input, one output. So you can see I'm predicting y from the x, and this is a regression. Of course, this do not only limit to a single input. We can also apply that for multiple input as x. But still, we are predicting one value, y. And that actually is an idea. This very simple idea will be correlated to a lot of chemical properties. And one of the simplest example of like applying this linear relationship concept in chemistry is the so-called Hammett equation. So Hammett equation is basically representing the property of a substituent on a phenyl group is by this reaction. So I'm basically judging the electronic property of this phenyl group by its effect to the dissociation of benzoic acid. So I'm trying to attach a functional group to benzoic acid, and I want to see what is the change in the acid dissociation constant. And the power of this Hammett equation is that it does not only apply to this acid dissociation reaction. We can also apply that to some other related reactions, also related to the substituent effects of this functional group. Now, if we do that and we try to apply that to different substituents, and then we also fit that for different reactions, then if we have a combination of substituents and reactions that we haven't seen before, say we have never tried to make a chloro substituent in the para position for a particular reaction, if we know the coefficients for the substituent, or say chlorine in a para position, and the reaction, say for some other reactions, then we can use this relationship to make predictions. Okay, we can actually predict the equilibrium constants of this new reaction. And that is the power of this Hammett equation. And this general approach is often called the linear free energy relationship. So you can see it is basically based on linear regression. And although this sounds like a very similar idea, it is already good enough for a purpose like catalyst design. So there actually published work, this one I picked an example from the segments group, on using multiple linear regression for catalyst design. So the general idea is there are many things, like many substituents, we can tune on a catalyst. And sometimes we do not know the actual effect of all these substituents to a chemical reaction because they may affect a certain step in a non-trivial way, like this one is by some sort of non-covalent interactions. However, we only need to know that when we change these functional groups, there will be a certain effect with the substrate and that affects the yield or selectivity. And we are basically using a statistical model to describe the relationship between these functional groups and the outcome. So here, even if we do not know anything about the actual reaction mechanism, we can still use a statistical model to make predictions. And also that statistical model may lead us to understand what is the underlying mechanism. So that is the idea or the power of this using a cheminformatics approach to study the reaction or study catalyst design. So in this reaction, well, because we are trying to tune the fragments and trying to get a certain outcome, then we need to represent fragment properties. So in this work by the segments group, the steric and the electronic properties are represented basically by stereomole parameters and also vibrational modes. So the stereomole parameters are basically talking about the width and the length of the substituents. So this one you can see, okay, the long axis, the short axis, and also the length of the substituents, you might imagine they're related to the steric properties. For the electronic properties, instead of actually talking about some charge distribution, they actually choose the vibrational modes in terms of their frequencies and intensities. So you may imagine, okay, if we have electron withdrawing group, electron donating group, then they will actually strengthen or weaken the bonds, some of the bonds, and that will affect the frequency and also the intensity of a certain vibrational modes. So these are some ways that you can use to represent the effect of a fragment. Now, with that, then you can actually use that to describe a different kind of substituents, different kind of modifications you can make to a catalyst. And then you can make a prediction. You can see, well, we can get a reasonably good predictions based on all these complicated properties. Basically, different kind of frequencies, intensities, some length, width, and stereomole parameters. So if we combine all of them in this complicated model, then we can actually make a prediction. And this prediction will give us a good predicting result and will actually make further guidance to future reactions, to future experiments. Now, you must say, okay, that's good, but that is only part of the story. In order to make a valid prediction, before we actually apply the model, we should first validate the model or evaluate the performance. What does that mean? Well, if I give you this picture, you can see, okay, there are some blue points here, and I give you two models to model these blue points. One is this green line, the other is this red line. Well, I think most of you will think that, okay, green line is a better model, not the red line. However, you can see that this red line actually has zero error in terms of predicting these blue points because they are passing through all the blue points exactly. Now that is the question. Even though this red line are basically passing through all the blue points, why do we think that that is not a good model? Why do we think that green one is a better model? That actually leads us to the concept of overfitting. So what is overfitting? Well, let's reproduce this example, say if I have a data set like this, then I can model it. Well, visually you will see a curvy relationship. So of course, if I do not visualize that, I may start with a linear regression, so I get a linear model. And if I visualize it, I see this curvy relationship, I may use a quadratic model. Now you can see that this quadratic model is fitting much better than a linear model because all the blue points are close to the red model. And for the linear one, it is not the case. Okay, for the linear one, you can see there's some large deviation from the red line. However, if I give you the third model that looks like this, you will see that even for the quadratic model, we still have some deviations here. We still have some deviations, we have some blue points that are not lying very close to the red line. But if I'm looking at this model, you can see all of the blue points are very close to the red line. But based on your intuition, I think most of you will agree that this is not a good model. Why? The underlying reason is that we want a model to work for both the observed data and the unseen data from the same distribution. And this actually will not apply. What does that mean? Well, if we try to get some other samples from the same distribution, say we get some data points like this, then we can apply all this model fitted on these blue dots and try to use them to predict these yellow dots. Now we can also start with a linear model. You can see, okay, it's not making a very good prediction because the yellow dots are still deviating a lot from the red line. And the second, the quadratic model, you will see that these two models, no matter applied to the blue points or the yellow points, they have similar performance. However, for the third model, that it applies well to the blue dataset, it will not apply nicely to the yellow dataset. You will see a much larger deviation in this case, much larger deviation. Although, if I look at the dataset, they basically come from the same dataset. But if I'm using only the blue points for modeling, and I want to use that to make predictions on some unseen data, that will not be a good idea because I actually make poor predictions around this region. So this observation will actually help us to identify a situation called overfitting. What is overfitting? Overfitting is that the model is focusing too much on the seen data so that it does not generalize to unseen data. Like this red line is over-optimizing for this blue dataset, so that even though the yellow dataset comes from the same distribution, the yellow dataset is poorly predicted. And for the other end, if we see, okay, these two cases for the linear model, well, they still perform similarly, just similarly bad, then that is called underfitting, because you can see I can improve the predicting power by increasing the complexity of the model, turning from the linear model to a quadratic model. At the same time, if I'm using quadratic model, it still generalizes well, because a quadratic model or built on the blue dataset will still apply nicely on this yellow dataset. So if they are equally bad, they're called underfitting. If the performance of the two deviate a lot, that is an indication of overfitting. And that is the idea. How do we judge the performance of a model? And this method is called the model validation. Basically, we want to divide our data set into the training set and the testing set. Because we are talking about seen data and unseen data, but the unseen data, that means we need to do new experiments. Sometimes, because of cost limitations, so we cannot do that. Then how can we make predictions? We basically divide all the known data points into two groups. One is called the training set, the other is the testing set. And we are basically using the testing set to evaluate our model. So the general idea is that if we have a data set that is like this, then we want to split this data set into two sets. One is called a training set, one is called a testing set. Of course, often it is not a one-to-one ratio. Often we have a larger training set, a smaller testing set, like 2-to-1 or 4-to-1, something like that. then we are basically training our model on the training set and then compare the performance between the training set and the testing set. So this one basically is a quadratic model. You can see the red line is built on the training set, the blue points, but it also performs well for the testing set, the yellow points. So the model based on the training set can generalize to the testing set. But for this wiggly line that is overfitted to the blue dataset, the training dataset, you can see that the performance is good for the blue dataset, but the performance is quite bad for the yellow dataset. Okay, the performance, they have actually quite a large difference in terms of performance. So this model based on the training set cannot generalize to the testing set, and that is an indication that you are overfitting your model. Also, this is not good, so we should try our best to have a consistent prediction or consistent performance between the training set and the testing set. So you can see, we can also apply this idea to our catalyst design. You can see, in fact, in this model by the Sigmund's, in this work by Sigmund's group, you can see we do have validation set. So you can see these red points are basically a validation set. You can see they do have similar performance. So those training set and the validation set or testing set, they have similar performance. So that is good. And similar idea was also illustrated with some other work, like this work from the Biol's group. So you can see a very similar idea in ligand design. So this one is basically for nickel-based catalysis. And the idea is that if you try to model the steric effect of this ligands using the so-called cone angle and also the percentage buried volume, then you will capture something called the remote steric effect. Basically, the difference between these two, although both of them are steric hindrance measure, but if you are talking about the cone angle, basically you are having a cone that extend to infinity, then you are trying to use a smallest angle to enclose the whole ligand or the whole substituents. But for the percentage buried volume, is basically the occupancy up to a certain radius. So it is basically the steric hindrance of a close proximity, while the cone angle is capturing the steric hindrance in general up to infinity. And you can actually measure the both parameters, the percentage buried volume and also the cone angle for different ligands, for many different ligands. And you can actually also use that, very simple parameters, to make predictions, okay, to make predictions on the yield. And based on that, they actually have seen the so-called remote steric effect, because you can see the effect of steric hindrance, even though they are very far away, okay, even though they are very far away. So this is another example of using the so-called multiple linear regression in catalyst design. Of course, linear regression is a very simple model. You can also extend that to a more sophisticated model. So linear model is just the starting point, and there are more sophisticated model which takes into account nonlinear relationships. And you can see that the choice of this model will also relate to how do we represent our chemical information. As mentioned before, actually the information, representation, and the regression model, they're all interrelated. So say for this benzoic acid, we can represent that with molecular descriptors like fingerprints that we mentioned, or some other descriptors based on experiments, or some topology related descriptors. Then all these, because they are numbers, the focus are basically numbers, then there are certain set of techniques that works well for numbers. Basically, there are random forests and some other like support vector machines and some other methods. So we'll also briefly talk about the random forest as an example for all these kind of prediction methods. However, for the same benzoic acid, you can also represent it with a graph, basically by the Lewis structure or SMILE string. And using a SMILE string or the molecular graph, you're basically capturing the connectivity information. So this connectivity information and the topology of the molecule, they could be used in some other models. Many of them are represented by neural network-based model because a lot of neural networks, they're quite compatible with a graph structure. So they can actually make good use of this graph structure to make predictions. And we will also briefly mention a method called message passing neural network. So these are just some examples of prediction models beyond regression, beyond simple linear regressions. So let's start with random forest. What is a random forest? Random forest is basically a prediction by a forest. And a forest, you can see, is basically a collection of trees. So in this case, this collection of trees is actually a collection of so-called decision trees. Decision trees are trees like this. Basically, you are asking a question. You have two or a handful of answers. You want to predict whether you want to go out and play. You want to consider the weather, the humidity, whether it is windy outside, and so on. So every question you actually lead to a certain answer. Maybe you want to play or you don't want to play. And you can see we can actually make predictions based on the very simple yes-no questions. And we can generalize this. We can build a lot of models, some based on weather, humidity, some based on humidity only, some based on whether it's windy or not. Then we can consider a lot of models, a lot of decision trees. These decision trees, they represent different kind of picture because some are more focused on certain parameters, others are focused on different sets of parameters. And we take a collection of them and we either take a mean or use a voting procedure to determine the majority prediction. And we pull all these kind of predictions together. This is the idea of random forest. Basically, we have some models focusing on some properties. Of course, this one is about predicting you're going to play or not. For molecules, maybe some of the questions are about whether you have a certain hydrogen bond donor, whether you have more than 5 oxygen atoms, whether it is soluble in water, and also some combinations of them. Then you can have a lot of decision trees. And these decision trees, they will make some predictions. And we can collect the predictions of all these decision trees to make a prediction, make a collective prediction that is called random forest. This is a general idea of using properties, using different properties and put them together to make predictions. The good thing about this decision tree or tree-like method is that you can actually trace the logic. You can actually see, okay, what is some dominant factors, and then you will see, okay, because judgment is based on this, so I can try to tune certain experimental parameters. Okay, and another big class of methods are neural networks. Maybe you have heard of the word neural networks in some other fields because they are quite important in the recent years in terms of like ChatGPT, in terms of like Midjourney. We have like text prediction. We have like image generations and some other related applications. So they are all neural networks. The word neural networks comes from the fact that they are actually mimicking an actual neuron. So sometimes they also called artificial neural network to distinguish from the biological neural network. And we are basically representing a neuron using a mathematical model like this. But they have a similar idea in the sense that we have a weighted sum of all these inputs, just like we have a dendrite. Basically, they will collect different inputs. And then these inputs, they're pulled together and then they're weighted. And then if all these input signal, they sum up to a certain threshold, then the neuron will fire, basically passing the information to the next step. So they're basically passing the information to the next step. Otherwise, they will not fire, basically passing a 0 to a next step. So with this simple structure, we can assemble them into like layers. We can assemble them between like inputs and some other nodes. We can assemble all these functions between the nodes, and then we can assemble more. And this is the so-called neural network. And we can also assemble more layers. And if you have heard of the word deep network, or nowadays you might have heard of the so-called deep seek. And the word deep is basically based on the fact that you have a lot of layers of these neurons. And you have a lot of layers, you have a so-called deep network or deep neural network. So that is the idea of a neural network. And if you are interested in understanding the mechanism of this neural network, how do we sum up informations from inputs and then fire and then make predictions. You can actually go for this like online platform. This online platform, you can actually try to put in different inputs and then see the predictions. You can have predictions, binary predictions like called classification, or you can also have regressions. So you will see actually how each neuron will be combined together in different layers and then make the final predictions. And there are actually more structures nowadays. This is actually an old example, but there are many more kinds of neural networks with different mechanisms, different architectures. But the general idea is still based on a neuron and how do you aggregate the information, how do you pass them to the next layer, and then how do you assemble them together. Now, in chemistry, one of very popular architecture is called the message passing neural network. Basically, you will attach information about the atom and also the edge. Okay, the edge are basically the bonds. So for atom, you can have some atomic properties like which kind of atom, atomic mass, or electronegativity, or some other properties. And then for the edge, you can also have like bond order or some other properties, bond distance. And this information, they are basically connected by neurons. You can imagine similar neurons. They will actually pass information around. So I can look around the information around an atom, or look around the information around an edge, basically a bond, and then we can aggregate the information of the neighbors and then pass them around. And then basically we are having this message passing procedure and updating information after we go through a several steps. Then each vertex or each atom will actually contain information that is not only related to the atom itself, but also the chemical environment around. And when we have that, then that will be useful. This kind of representation will be useful for further classification or regression. If that sounds very complicated to you, you can also imagine how do we determine the so-called field effect of a substituent in a molecule. So basically, we'll see, okay, look at the proximity is basically one atom around, two atom around, and then we will determine, okay, whether that effect is like polarizing or not, what is the magnitude of that effect. Basically, if you try to pass around this information, you will say, okay, the field effect of this functional group to this atom, and then this effect will also pass to the next atom. Then you go through all this procedure, then you will also get a representation related to the chemical environment. So this similar idea actually mimics how we determine the chemical effect based on the chemical environment or the neighboring atoms or neighboring functional groups. The only difference is that we are using a neuron or a mathematical model to do this automatically. Now you can see all these methods, they are actually quite powerful, and they will, in certain sense, capture some of our chemical intuition. And in fact, all the development of all these neural networks are a very hot topic in the recent years, as represented also by the Nobel Prize in Physics and also Chemistry in 2024. So you can see the Nobel Prize in Physics in 2024 are awarded to two scientists who actually work on the application and also the underlying mathematical theories of neural networks. And as mentioned in the beginning of today's talk, the Nobel Prize in Chemistry is about the application of all these mathematical models. So you can see how they are actually impacting the development of frontier science. Now we are moving to the final part of our discussion. So the final step about making prediction after we make predictions, then that prediction should guide our future experiment design. And this is actually not a very easy step in the sense that experiments are often costly. So we want to obtain more information from a limited number of experiments. So when we are trying to propose an experiment, we should propose experiment that will actually bring us the most amount of information. Again, we want to lower the cost and increase our success rate. And in that case, we can actually make an analogy against the story of the blind man and an elephant. You can imagine, okay, if there's like a certain number of blind men and they want to see what does an elephant look like, then these elephants, they can try to touch the elephant from different parts. Although it sounds like a joke that they do not have a consensus, but at least that will be better than if all the blind men are touching the ivory, and then they would just think, okay, the elephant is something that feels like a carrot, which is not the case. But if they actually touch different parts of an elephant, if we aggregate the information of all these blind men, then we will actually have a better picture on what an elephant looks like. Now, for our case, the elephant is basically the chemical space. We do not know our chemical space, and the blind men are basically different experiments. We want our experiments to be spread out. They're sampling different parts of a chemical space so that we have a better idea on what a certain property will be exhibited in different parts of the chemical space. So to cover the chemical space, sometimes using commercial product might not be good enough. Like for ligand design, commercial ligands might not be good enough to cover the chemical space. Here I'm picking an example from the Denmark's group. So here you can imagine this is also an example of a ligand design. So this is a chemical space of all the possible ligands based on a certain criteria. And you can imagine that the commercial ligands are only covering part of this chemical space. So most of them are in the central part. And you will imagine, okay, those commercially available ligands should be easy to synthesize and they share some sort of similarity. However, you can see that some parts of the chemical space are underrepresented. Some part of the chemical space you do not see any green dots around. So if you are actually designing an experiment, then you should consider whether you want to cover nicely all the parts of the chemical space. In that sense, you should intentionally pick some ligands from this region so that you can have a better probe on the chemical properties around. Okay, so to do that, actually there is a method called clustering. So basically we want to find groups that are similar to each other, and basically we want to pick some representative sample from each group or the cluster centers to cover the whole chemical space. Okay, so that is a method that if we want to make good use of our information, make good use of our experiments, then in the design, we want to cover different parts of the chemical space. Now, and that is only part of the story. When you are actually achieving a chemical goal, then some predictions might be different from existing ones, so from existing experimental records. So sometimes you need to have some trials, and at the same time, some predictions that is theoretically good may not be realizable by experiments. Say if you say, okay, the ideal number of carbons in a functional group is 2.5. That does not make sense because we either have an ethyl group or a propyl group. We do not have a group, we do not have a functional group with only 2.5 carbons. But theoretically, maybe you will have a prediction that is like a number 2.5, then that theoretically good prediction may not be realizable by experiments. So you need to do some approximation, you need to make some decisions, and at the same time, the predictions and experiments should go hand in hand. So sometimes you need to go through a cycle. So your cheminformatics procedure will make some initial predictions, and this initial prediction will be fed into experiments, and these experiments will give us more information. From this like extra information, we will try to make new predictions until we get our final goal. So this might be an iterative procedure. Okay, so this is basically the whole idea of a cheminformatics workflow. Now, in this part of the talk, we want to walk through a hands-on example. So we actually want to go through all these steps and see how it works out in a real example. However, because we are not doing experiments now, so we will leave out the final step. But we will try to go through all the steps in front to see how do we actually get data, represent them, look at their similarity, visualize them, and then make the prediction model, validate the model, and so on. So the example we will work with is the lipophilicity of the molecule. And we want to predict the lipophilicity based on Lewis structures. So the only input is Lewis structure or smile strings. and the prediction, it should be a lipophilicity. So why do we choose lipophilicity? At least this is a useful property for drug design, and we have the dataset lying around. So if you still remember the Lipinski rule of 5, in the Lipinski rule of 5, one of the rule is about lipophilicity. That lipophilicity is represented by the water octanol partition coefficient. So we will do the same thing. We will also try to predict the water octanol partition coefficient. So partition coefficient is basically something like if you try to put two immiscible solvents together and then put in your solute may dissolve partly in one of the solvent, partly in the other solvent, and you want to compare or basically take the ratio of the solute dissolving into two solvents, and you can actually quantify the relative likelihood for the solute to dissolve in these solvents. Okay, and there's a data set of called Lipophilicity that you can actually download from the Molecule Net, which is an online database containing a lot of like physical properties. So there's a Lipophilicity dataset that you can simply click and download. And if you download the dataset, you can actually get, you can open it with Excel or some other spreadsheet software. And then you can see, basically there are only 3 columns. The first one is just an ID. The second one is the experimentally measured partition coefficient. And the third one is the smile strings. So basically you have molecular ID, the partition coefficient, and the smile strings. So we want to predict the second column using the third column. Okay, the first column is only for labeling, is not for prediction. Okay, we should predict the second column, the partition coefficient, based on the smile string. So before we make any predictions, we can actually visualize this data set. We want to see, okay, whether we see certain trends so that we can make use of, and whether, in theory, we can make some good predictions. So in that sense, we first will visualize the data set using the same online platform that we have mentioned, this ChemPlot. This online platform, you can actually upload your data set. So you can upload your data set here, and then you can actually see the file. So this file, you can still see the ID, the partition coefficient, and also the smiles. And you can actually select the columns because some of the similarity measures will be based on also your predicted property. So you need to select the correct columns so that you can make a proper similarity measurements. And we can also use principal component analysis because, well, it can better preserve the global trends. And then we will use a principal component analysis to visualize this dataset. So if we project that with a principal component analysis, you will see a plot like this. So this color bar is indicating the partition coefficient. And you can see, we can actually see trends in these projections. So the neighboring dots do have similar colors. So you can see neighboring dots do have similar colors. And we can see the darker ones or the more negative ones on the left-hand side, the lighter ones on the right-hand side. So again, we can still see trends. At the same time, we can see some data points that are lying far away from the main group. So why? Well, they could be outliers. They could be some other reasons. So it's better for us to visualize them. So if you actually do that in ChemPlot, so you can actually put your mouse here, and then you can see, okay, what are the outliers here? Okay, so this is the idea of visualization. And then you can also see a general trend. You can see some of the regions are poorly sampled, some of the regions are nicely sampled, and you may want to see, okay, whether you want to examine those poorly sampled regions or not, and make your decisions. Okay, then after you have a general idea of the data set, then you can actually build a statistical model. To build a statistical model here, we are using the so-called Jupyter Notebook here. Basically, it's a Python app that could be used to code on a web browser. So here we are using a service on Google, which is free. At least for most of the purpose, it is free, except you need to have a very lengthy calculation. Otherwise, for most of the Cheminformatics purpose, then, well, you can simply use the free online resources for the calculations. So you can actually code based on Python on this notebook. But for this case, for this example, you can actually download the notebook from the Synthesis Workshop website. And after you download the notebook from the Synthesis Workshop website, you can actually upload it to your account. And when you upload that to your account, you can run the cells. You will see all the comments, but we will actually walk through what's going on. So here you can see, well, first we will load the packages, we will load the relevant functions. And if you want to run this part of the code, you can just put your mouse here to this like square bracket and then click it. You will see this like triangular sign that basically it will run. And after some time, you will see a check mark next to it. Then that's basically like you have finished running the cell. Or you can click Control F9 to run all the cells like sequentially. And here, basically, the first step is just loading the relevant packages and then loading the relevant functions. And that is basically preparing all the Python functions. And then you will start to load the dataset. Here, it will automatically download the dataset from the website, from the MoleculeNet website. And you will also be able to visualize the dataset. Again, you will see the entries. And also, you can render the Lewis structures. Okay, this is another cell rendering the Lewis structure. Now you will see that, okay, they're actually quite different, so you might not see the similarities between them, but you can also go back to the chem plot, and then you will see, try to figure out, okay, whether there are some similar structures lying around. Now, because we are trying to predict the partition coefficient based on the smiles, the smile strings, and you can see smile strings is like text, so that is not very friendly for a numerical prediction. So we will actually first compute some molecular descriptors. So there's a list of like molecular descriptors available with the Python package RDKit. And some of them you can see, well, it's like molecular weight or the Lipinski hydrogen bond donor or acceptor number of heavy atoms. Many of them are kind of self-explanatory. So we'll actually calculate all these descriptors using a function like this. So we will convert from the smile strings into a series of numbers. And then we will actually make all our later predictions based on these numbers. Basically, the number of atoms, number of hydrogen bond donors, and so on and so forth. So this is the computed result. So each entry now is appended with different numbers, like a lot of numbers. So these numbers, like the later part of the descriptors, we actually have a lot of columns here. Now, after you calculate the molecular descriptors, we'll actually put all these numbers into a later step. We'll start with splitting the dataset into the training and testing set. As mentioned before, we should validate our model, or to evaluate our model, we should evaluate based on a dataset that is not used in the training. So here we are using a testing set to evaluate our model. So we should first split our model into two sets. Then we can say start with the simplest one, the multiple linear regression. So multiple linear regression, we have a prediction in the training data, and then we also use the same model for our testing data. You will see that actually they still have a slightly larger area for the testing data, but it's still kind of acceptable. So you can see how the simplest multiple linear regression could give us some sort of prediction in the testing data. So we can actually use the computed properties to predict the partition coefficient to a certain accuracy. Of course, that is not very satisfactory. This is not a very good predictive power, so we can extend our model. So here in the notebook that is available on the Synthesis Workshop website, we actually include several other models. Apart from the multiple linear regression, we also included lasso and also the decision tree. But you can try it out yourself. But we also have the random forest. Remember, random forest, we are actually pulling many different decision trees together to make predictions. But here you can make a simple comparison between the multiple linear regression and the random forest. You can see this random forest is actually giving us a much higher predictive powers. You can see the points are lying much closer, to the to the ideal situation. Okay, this orange line is indicating the ideal case where the predicted number is equal to the experimental value. So you can see here we can have a much better prediction. At the same time, you can see the testing data is actually fatter. So there's also some sort of sign of overfitting. So you can actually tune the parameters so that they look kind of similar. So there are a lot of things that you can tune in order to get the best result. And after you actually get the best result, you can make a prediction of an unknown molecule. Of course, I think this like aspirin molecule is also available in the dataset, but say if you want to predict some other unknown molecules, so you can just put in the small strings here, and then you can make a prediction. So basically you are fitting in a new molecule into your statistical model, and then you want to get the new properties and reactions. And in this case, basically we are putting in aspirin molecules. The aspirin molecule, we use the property getter to obtain all these properties that could be directly computed from these smile strings or from the Lewis structure. And then these properties, these molecular descriptors, will be fed into, say, a linear regression model or a random forest model. And then we use a random forest model to make our predictions of partition coefficient. So this is how we use the whole model. Basically, we use a lot of data to fit our statistical model, and then we validate them. And after we have a validated model, we can use that to predict properties of a new molecule. So that is the whole idea. And hopefully you get a much better idea into the rationale of the cheminformatics workflow, and also work through the example. Hopefully you know all the procedures. So if you want to know more about cheminformatics, there are also a lot of useful resources online. There is actually a GitHub page by someone else that you can find a lot of information on different aspects of cheminformatics. Okay, this GitHub site is called the Awesome Cheminformatics. So you can see applications on visualizations and docking and some other things, different information about different libraries, and also some books or blog posts that are kind of useful for like getting an in-depth idea into different aspects. Okay, so that is basically all I want to share on the introduction of cheminformatics. Okay, this talk is not possible without, of course, the invitation from the synthesis workshop team, and I would like to thank for their kind invitations, and also I would like to thank my home institution for supporting me for actually having a course in cheminformatics, and also my students and some of my friends who actually give me constructive comments on this talk, and also my original course that is held on the Hong Kong University of Science and Technology. Of course, last but not least, I would also like to thank you for your kind attention. Thank you very much.
Thank you, Frederick, for this in-depth crash course. If you've enjoyed this episode and would like to support our podcast, please consider following us here on YouTube or following us on Twitter. Thanks again for joining us, and we hope to see you next time.